Okay, let's we'll continue this slide and we'll go to reliable data transfer, which is the underlying concept of TCP. So the first slide is like this. We already mentioned this concept before. Okay, we have application layer and transport layer. There should be a sending process and a receiver process at the application layer on the receiving host and the sending host. Okay, those process will try to send the message to send the messages, right? So logically, the message will be transmitted between the sending process and the receiving process. And for TCP, the transport layer should provide a reliable channel for this message to send from the sending process and received in the receiving process. So basically, the actual route should be like this, right? Those processes do not directly send message to each other. They send the message to the underlying transport layer, and the transport layer should provide a reliable channel. So every bit you send from the socket will be pop up at the receiver's socket, right? So that is the idea. But however, as we mentioned before, all along the line, layer 3, layer 2, layer 1, they are not reliable. They are unreliable channel because the packet can be lost can be dropped, can be lost in the internet, can be dropped by the routers. The communication link could be very unstable. So basically, the underlying layer 3, layer 2, layer 1 is unreliable. So right here, the transport layer should play a role that the left-hand side, the blue one is the reliable data transfer protocol, which is a program in your operating system. Okay, it receives the data from the up layer, application layer, right? The message comes from here, and then it will pack the message to a segment, right? So the segment will be delivered to the underlying IP protocol right here. But at the right hand side, there should be another program at the operating system of the receiving host, the reliable data transfer protocol at the receiving side. It receives the packet, the datagram, from the underlying layer 3 IP layer. But there's one thing is that the received packet, it may have bit error. It may encounter packet loss, so it will never show at the receiving side. There are a lot of different problems will be caused by the underlying unreliable channel. So these two programs, left-hand side the blue one and right-hand side the green one, they should come up some mechanism to recover those lost packet, to deal with the bit error problems, to deal with the out of order problems, something like that. So those two programs should, and indeed they are very complex. Okay, so after that they deliver the message to the receiver's process, and the receiver process will have an illusion that the underlying transport layer is very reliable, although actually the underlying layer 3, layer 2, layer 1 is unreliable. So these two protocol at the sender's operating system and the receiver's operating system, they should come up some very complex algorithms and mechanism to to solve these problems. Okay, so RDT stands for reliable data transfer. Okay, so right here again, it is almost the same figure, but there's two important terms that you should notice. That when the sending process send the message to the sender side transfer protocol. Okay, usually it calls an API, which is RDT send. So basically, the message comes from the upper layer. So we call, and we use the word called from above, right? RDT send is a function that called from above, okay, by the application. So pass the data to deliver to the receiver's upper layer. Okay, the other one is at the right hand side right here, is called from below. So when the message arrives at the receiver side, okay, the layer 3 programs will called receive. Okay, so the right hand side, the green program will receive the segment. So we use the word call from above to describe such kind of situation. Okay, so the most important things you have to remember: call from above and call from below. Okay, and again, you have to remember that there are some different functions will be called. For example, right here, if all the messages is okay, and you call deliver data function to deliver the message to the receiving process. Okay, so right here, so when you send the segment to the underlying layer 3 protocol, okay, you simply just call send. Okay, you did send to ask the underlying protocol to transmit the packet, the segment for you. Okay, so make sure you understand there are several different terms right here. Okay, before we introduce a different communication protocol, I have to talk about one mechanism, one tool named finite state machine. Okay, because TCP is very complex, so we will not introduce TCP directly. In this textbook, we will introduce several simpler protocols. Okay, as shown here, there are RDT version 1.0, version 2.0, version 2.1, 2.2, 2.3, 3.0, and then we will introduce the exact behavior, exact operation of TCP. But still, it is very complex to introduce such different communication protocol, different design. So we would like to introduce a finite state machine. It helps us to understand more easily to understand how a system works. Okay, so finite state machine is used to describe the behavior of a system. So think about one thing: when you write a program, okay, and at any arbitrary moment, okay, you intercept, okay, the program, you start the program. What is the state of this program right now? Basically, we will use all the variables and its values to describe the current state of a program, interrupted program, and as well as we will use the program counter. The program counter means which line of code currently the program is running. So basically, we use all the parameters and its values and the program counter to describe the current state of this program. And it's very similar and like a vending machine. Okay, how do you describe the behavior of a vending machine? Usually, we will describe what is the state of this vending machine. Basically, we use all the amount of goods in the vending machine, right? And as well as the coins in the vending machine to describe the current state of this vending machine. Of course, a system should have a lot of different input and output I/O, right? So for vending machine, the input-output interface is the bottom on the vending machine, right? And as well as the coin, the number of coins you insert in this vending machine. And again, there should be the button that you can you can get all the coins back, right? So there are several different input and output to a system. For example, vending machine on those buttons, those coins, those buttons, return buttons, right? And you can get the goods you would like to buy, right? That is the input of a machine. And the state of the vending machine is the number of goods in the vending machine and the coins, the amount of money has been inserted in the vending machine, right? That's how you describe a state of a vending machine. And for program, the state, as we mentioned before, is the current variables, those values, and the current program counter, that you can use these things to describe a program. So it's the same right here. When you want to describe a very complex behavior like a protocol, okay, we simply just use a state machine to describe what is the state of this program, or what is the state of this protocol, and what is the input and output event can be observed in this system. So right here, when we like to describe a system, usually you have to specify how many different states this system have. Okay, for example, that's a very simple example. We have 2 states to describe a system. Okay, and you have to figure out how many different events that you can observe in this specific system. So every time you observe a new event in your system, okay, your state may change, or we say transit, okay, from one state to the other state, because you observe certain input or you do something output. Okay, so the event will causing the state transition will be written on the above of this line. Okay, this line. Okay, so when you do such kind of transition, there might be some actions should be taken when you do such kind of state transition. So basically, you have to write down all of your events, you write down all your states, and to specify the transitions between different events and states. Okay, I think it is a very interesting and very important tools for you to organize your own program or organize a very complex behavior. It is not only used in the protocol design. When you design for example, a very complex website, a very complex, for example, a business website, maybe in your mind, there should be several different states or several different procedures, steps to accomplish the entire application. For example, when you buy a book, you have to add your book into your shipping cart, and then you have to log into your account. You have to specify the address of the shipping address so that they can calculate the shipping cost, and then go to the for example the credit card web pages. Okay, so after the verification, then go back to the for example, the deliver page, so that you can know when your book will be delivered to your home, something like that. Basically, it's a very complex procedure. So we have several different steps, several different procedures. So you can use a finite state machine to specify how many different states you have and how many different input output we say interaction that the user can interact with the system. So for example, usually we will draw a transition table like this. Okay, you simply just write down how many different states you believe your system has. So something like that. Okay, and you can write down like this. You can write down how many different events or interaction that your system can observe. Or for example, E1, event 1, okay, event 2, event 3, event 3, event 2, event 4, something like that. So you can easily convert such kind of transition matrix, okay, into a finite state machine. So for example, let's write something right here. Okay, so you can see that I have a state 1, I have a state 2, right? So it says, okay, at state 1, when you observed event 4 and then goes to state 2, when you at state 2, right, when you see event 1 and go back to event 1, and of course we can do this, right? If you observe an event and stay in the current event, don't move, and state k, for example, that is 3, right? And so on and so forth, so on and so forth. So in this case, you can have a big picture of your system to see if there's anything wrong. So if there's any state or event missing in this state transition matrix, and you can check out that, okay, you can see that at state 2, only 3 different events will be observed in these systems. So you can think about, okay, if there is something missing right here, or okay, that is the state and the event I would like to this system should be. So you have the opportunity to check if this state machine is complete or is correct. Okay, but usually when we design the protocol, usually we will have another new state called state error. That means you know, because the communication is the message exchange between two peers, two remote peers. Usually we don't know what exactly the remote peers will do, because it might crash, it might act normally, it may we don't know, have bug. The program running on a remote server may have bugs. So usually sometimes we don't know what exactly the server will react to our message. So sometimes we have a error state. So you have to think about, what if something wrong? So usually we write it others. That means at state 2, if you observe any other events which is not E1, E2, or E3, it could happen because although it is not what you expect, but sometimes it did happen. You receive certain events that should not be observed at S2. So you should define some transition like others. So when you receive such kind of other events at state 2, you should go to state error, right, and try to figure out what's wrong with it, what's wrong with this specific event, okay, and see if you need to go back to state 2, or that is a very critical errors or critical problems that you cannot recover. So you then go back to the initial state. So usually we have this dotted arrow that specify the initial state. Maybe you have to do something like that. Okay, so I think it is a very useful tool for you to design a system. So right here again, we will introduce several different versions of communication protocols, and we use a finite state machine to describe how they interact with each other. So that is the very basic one, is RDT 1.0, version 1.0. Okay, that is the most easiest one. Okay, so because we have sender and receiver, so left hand side is the finite state machine of the sender, right hand side is the receiver's finite state machine. Okay, so let's take a look at this one. So as we mentioned before, when we design transport layer protocol, the blue part and the green part, okay, usually we will think usually the underlying layer 3, layer 2, layer 1 is unreliable channel, right? So we have to help the peers to exchange packets, right, correctly and normally. But the underlying unreliable channel may drop the packet, may do something strange, right? So, but the very first communication protocol we'd like to talk about is we assume that the underlying channel is perfectly reliable, and then we will release such kind of assumption, okay, so that we know how real internet works. But at the first place, we simply just assume the underlying channel is perfectly reliable, so there will be no packet loss, there will be no bit errors. Okay, so right here is the finance machine of the sender, okay, of the sender. So right here. So as a layer 4 protocol, okay, the initial state is right here. As we mentioned before, when the layer 4 protocol will be triggered, at the moment that the layer 7 send a message from the above, right? So usually, okay, we say the layer 4 protocol will wait for call from above. So you know, call from above means the upper layer send a message to layer 4. So it's right here. The upper layer application calls the RDD sent, and here is the message, right? Here's the message right here. Okay, so that is the event you received. So what is the action you should do? As we mentioned before, we have a segment, right? So here is the message. So we have layer 4 headers right here. So the MAC packet right here means we'd like to create the segment. Okay, but we simply just use the word packet right here. So, and then this layer 4 protocol will send this segment to the underlying layer 3 protocol. So that is the only thing you need to do. Okay, so after we send this message down to the layer 3 protocol, and then we go back to the initial state, we stay in the current state. Okay, we wait for the next message sent from the upper layer. So that's very simple. The reason why it is very simple, that is because all the underlying channels is perfectly reliable. So there will be no loss, there will be no packet errors. So every time you send your you receive a packet, you simply just pack it to a segment and then further send it to the underlying layer 3. You don't have to do anything else, because the underlying layer is assumed, we assume that is perfectly reliable. So the packet, the segment you send, will be at the receiver side perfectly without any loss and error. So that is the design. So let's take a look at the right hand side. As a receiver, okay, you simply just wait for what? Wait for the segment has been sent from the underlying layer 3, right? So wait from call from below, and that is the initial state. Okay, there are only one event, that is you indeed receive a packet from your underlying layer 3. So there are two things you need to do. First, to extract the segment and get the MSG, right? And you deliver this MSG to your layer 7, right? To your layer 7. That is the only thing you need to do, because you don't have to take care about packet loss, bit error, because there will be no packet loss and no bit error. So it's something like the layer 4 design right here is like a very simple process that simply just forward the packet from the layer 7 to layer 3, and at the receiver side simply just forward the segment from layer 3, and then you unpack the message and send the message back to the layer 7. That the reason is there's no error, no packet loss. So that is perfectly reliable. But as we know, it is not possible that, because we use packet switching internet, so there should be some packet loss. And the underlying layer 3, layer 2, layer 1, the media, the transmission, they might have bit errors. So here is the RDT 2.0. Now we assume the channel with errors. So the underlying channel may flip bits in the packet. So the corresponding transport layer protocols at the both operating systems, they should come up some mechanism to try to recover those bit errors. Okay, so as we mentioned before, checksum is one of the good tools that can help us to detect bit errors. So in this RDT 2.0, we add the checksum mechanism in the sending side and the receiving side, so we can detect error. You have to notice that error detection and error correction is two different mechanisms. Error detection only need to know there's something wrong with these bits, and I know there's something wrong. But error correction means I know there's something wrong with these bits, and I know how to correct those bits. There are two different concepts. But right here, we are talking about error detection. The transport layer only need to know this packet has some error, and I can check it by using checksum mechanism. That is good enough. Okay, so how do we recover such kind of bit error since we know there is something wrong with it? And then we introduce another mechanism in RDT 2.0 as feedback message. If there's something wrong with the packet that the receiver received, the receiver, it's right here, the receiver should explicitly tell the sender that the packet is either okay or had errors. So the message sent from the receiver not simply just receive packet. The receiver need to send an acknowledgement packet back to the sender and tells the sender that the packet is okay, so then I send an acknowledgement, or we use the word ACK. Or if the receiver encounters certain bit error problem, and the receiver will explicitly tells the sender that the packet had error, so the message will be NAC, negative acknowledgement. It can be NAC or NAC, which is okay. Okay, and after the sender receives such kind of negative acknowledgement, and the sender will retransmit the packet again, so that they can recover from these bit errors. Okay, we'll talk about this later. Okay, so here is the specification of the RDT 2.0 for the fine state machine. So just follow me. Okay, that is the initial state, right here. So sender is waiting for call from above. Okay, that is exactly the same as the previous RDT 1.0, right? So the first one is the layer 4 protocol indeed receives the messages from the upper layer, right? So then it's the same. They create the layer 4 segment, right? But however, because we would like to introduce the checksum mechanism, so the H4 header, they should have a checksum value, just simply like what we introduced in the UDP, right? We should have a field that record the checksum value calculated by the sender, right? Okay, so the packet is a little bit different. We have checksum right here, and we send the back packet, the message packet, to the receiver. And at this moment, the sender will go to the next state, which is called wait for ACK or NAC, because the sender need to know the packet is arrived or has something wrong with this packet. So it stays at the wait for ACK or NAC state. So it stopped right here. Wait right here. Okay, so let's take a look at the right hand side. It is the initial state of the receiver. Okay, receiver is waiting for call from below, and right here, indeed, there's a packet arrives. That is the symbol that is called AND, right? And after the receiver calculates the checksum in this message, and then it figures out there's no bit error. So we use the word not corrupted, not corrupt. Okay, this packet is exactly the same as the checksum value is exactly the same as the checksum value in the checksum field. So we believe there's no bit error in this packet, right? So that is the event you received. And then here, it's the same. We unpack the messages and send the messages to the upper layer 7 program, right? But right here, we have to explicitly tell the server that this message you sent is correctly delivered. So we send an acknowledgement packet back to the server. So right here is number 3, right? Right here, the server wait. Sorry, it's not this one. Number 3. So the server waits at this state, right? And it receives the response, and the response is an acknowledgement. That means everything is fine. You send the messages, and I send the ACK, and you receive the ACK. So everything is done. That is good enough. So we do nothing. That means empty. Okay, that symbol is empty. Then it goes back to the initial state. Wait for call from above. So next time when layer 7 has messages to need to be sent, and the sender will wait for call from above state. Try to serve the next message, and so on and so forth, so on and so forth. So usually step 1, step 2, and step 3, so on and so forth, so on, and it keeps go on. And the server can, the sender and receiver can send many messages by go over these 3 steps. Okay, and now we will trying to now we will talk about this one, number 4. So when the sender sends a message, okay, so it will stay right here, wait for NAC or ACK. So there's a error situation is that when the receiver receives this message, and after checksum, but we figure out the packet has bit error, so we say it is corrupt. Okay, so the message, although the receiver received the segment, but the bit in the segment has something wrong. The checksum is not exactly the same as the checksum calculated by the sender, right? So at this moment, the receiver will send a negative acknowledgement, a NAC, back to the server. And meanwhile, the receiver will stay at the wait for call from below state. Because the message is not delivered, the message has something wrong. So state is not changed at the receiver side. But the receiver sent an explicit message, which is negative ACK, back to the sender. So at this moment, if this is number 5, right? If the sender receives a packet and the packet is NAC, and the server now realizes that the packet has sent to the receiver is not successful, has something wrong with this packet. So right here, okay, the purple one, the sender will send the packet again. You can see that it's SND packet, but that is exactly the same as this one. So basically, it is a retransmission. So, and again, if everything goes fine, then the server and the client will go 1, 2, 3. Server send messages, client send, sender send messages, receiver receive and deliver, and then send ACK back to the sender, and sender receive this ACK. Then everything is fine. But if there is something wrong, then the process go like 1, 4, and 5. 1 is send message. 4 means I don't know how to, I don't, there is something wrong with this packet. So at step number 4, I don't know how to deliver the packet. So I send a NAC. And number 5, so when I receive a NAC as a sender, then I do the purple retransmission. So this process will keep going until the receiver receives the correct packet. So it goes to number 2 and send the ACK back to the sender. And the sender will leave, wait for ACK or NAC, and go back to the initial state, wait for code above. So that is the entire finite span machine specification of RDT 2.0. Okay, so make sure you understand all those process and how what is the event encountered and what is the actions should be taken when certain state has is arrived. Okay, and it is a very simple one because we only consider right here, we only consider channel with bit arrows. Okay, and there is something wrong with this RDT 2.0. Okay, it's right here and here. There's something wrong with these two functions. When the sender gets the packet from the receiver, okay, it should specify the receiver received the packet correctly, or the receiver received a corrupted packet, right? So there should be a flag in the packet to indicate it is a NAC or it is an ACK, right? But right here, the assumption is that the channel might with bit arrows. So there's one situation not considered in this RDT 2.0 is that when the sender receives the packet from the receiver and open the packet and try to parse the packet to see if it is a NAC as in step number 5 or it is an ACK as step number 3. However, if there's something wrong with this acknowledgement, what if the sender cannot tell it is a NAC or it is an ACK? Because there might have bit arrow in this channel, right? So what if the messages received by the sender, it cannot tell it is a NAC or it is an ACK? So there's a fatal flow of such kind of design. Okay, so as we mentioned, so it's right here. What happens if ACK or NAC corrupted? So the sender cannot know what happened at the receiver. So the only thing that the sender can do is to retransmit the packet again, since it does not know it is an ACK or it is a NAC, right? But you have to think about one thing. Okay, if the receiver send an ACK, so it's step number 2, right? Back to the server. So receiver believe everything is fine, everything is done. Okay, so I deliver, it's right here. I deliver the message, so everything is fine, so everything is done, and I send the ACK back to the sender, right? However, if such kind of ACK acknowledgement is corrupted, so the sender cannot know the server indeed receive the message correctly, or the receiver does not receive the packet correctly. The only way that the sender can do is to retransmit the packet again, which is the purple one. But at this moment, when the receiver receives the retransmitted packet, the receiver has no clue that its egg is corrupted or not corrupted, because the receiver does not have any mechanism to know such kind of information. So when the sender sends the retransmission to the receiver, if the sender does not know it is an egg or is an egg, the receiver may confuse that, okay, there is another purple packet. The receiver cannot tell it is a retransmission or it is a next packet, but this packet is exactly the same as the previous one. Okay, so it is possible for the receiver to receive duplicated packet because the receiver has no information about the egg or neck is successfully received by the sender or not. Okay, so in this case, we need to deal with the this problem, the orange problem. Okay, the egg and neck corruption problems. So since we need to do such, we might need to do retransmission. So here is the mechanism, new mechanism introduced in 2.1, that the sender will transmit current packet if egg and neck corrupted. So the sender need to add a sequence number to specify this packet is a retransmitted packet or it is the next packet. So a receiver will discard, and that means will not deliver this message if duplicated packet received at the receiver side. Okay, so let's take a look at this one. It is more complex right here, so make sure you follow. Okay, that is the standards finite state machine. Okay, so right here it is the first, this is the initial state. Since we now have sequential number mechanism, so at the first place, the sender will wait for cofun above, but the message right here is number 0. So the first step is that, okay, the application there indeed send the message to the transport layer. Okay, so again right here we need to create a segment, right? The segment currently we have checksum mechanism, and now we have to specify that is packet number 0, and then we send the packet to the layer 3. So that is okay. And again right here, that is the initial state, right? So we wait for cofun below, but right now we are waiting for packet number 0. So if the packet arrives, so that is step number 2. So if packet arrives and there's no corruption, and it is indeed packet number 0, then we will deliver the packet to layer 7, right? And again, we will send an egg back to the sender. And again, this egg, now we have checksum mechanism on this egg as well. So we send the egg back to the sender. So that's step number 2. So right here, okay, right here. Oh, after the sender send the packet to the receiver, okay, the sender will goes to wait for egg or neck, right? And for number 0. So if packet arrives, so that is 3. Okay. if packet arrives, right, and the ACK, right here, the ACK does not corrupt, that means everything is fine. We simply just go to next state. The next state is we wait for call from above, but now we are waiting for packet number 1, so everything's fine. So that is. However, there are some other situation right here. If the sender receives a packet, but the packet is corrupt, so we cannot tell it is an ACK or it is a NACK, or we can explicitly know that is a NACK. So in this case, in these two cases, okay, that means the message delivered to the receiver is not actually delivered because we don't know because it is a NACK, or we don't know what is the situation because the ACK or NACK response is corrupted. So in this case, we send the packet again. That SND packet is exactly the same as this one. So that is a retransmission. Since we don't know what's going on at this receiver side, and we send the packet again. And this packet is number 0. So it is a retransmission. So again, at the receiver side, okay, at the receiver side, 5, okay, at the receiver side. If the receiver now trying to wait for the next packet, and it indeed receive a packet and it is not correct. However, right here, the packet number is not what I expect. But after sending the ACK of packet number 0, I'm currently waiting for packet number 1, right? But currently at step number 5, I receive packet number 0, so I know that it is a retransmission. So I know I don't need to deliver this packet again to the layer 7 because it is a retransmission. So the only thing you need to do is to send a ACK and corresponding checksum again back to the sender to ask the sender to move on to the sequence number 1. Because when server continuously send or retransmit packet number 0, that means it stuck in wait for a ACK or NACK 0. Only if it receives a correct ACK, which is right here, and it will move on to the wait for call from above number 1. Right? So at the receiver side, after you receive a retransmission, if you already receive such kind, if you already deliver packet 0, which is right here, if you already delivered packet 0, the only thing you need to do is to send an ACK again to tell the server, to tell the sender that you already received packet number 0. So we finish number 0, then keep go on for number 1. Okay, so as you can see that actually those these two different these two final state machine, they are symmetric. They are either expecting sequence number 0 or expecting sequence number 1. Okay, so that is symmetric. So we will not go over this part, but it is exactly the same as the right hand side. Okay, let's take a look at the last one. Okay, if you as a receiver, if you receive a packet and it is corrupt, then and again you need to send the NACK back. So you stay at the state and wait for 1, for example, right here. Okay, so the sender it is the same. It is symmetric. You are either waiting for, you are either waiting for 1 or waiting for packet 0. Okay, and in this case, because this part, okay, because this sender and the receiver, sender sends 1 packet and wait for the receiver's response. So we call this stop and wait. In this mechanism, we do not send 2 packets simultaneously. We send 1 packet and then wait for the response, which is ACK or NACK. And then, so in this case, we only need 2 number, 0 and 1. So if you finish the 0 round and then use 1 and expecting packet 1 and wait for an ACK 1. All right. And after you finish the 1 round, and of course you can use the number 2, sequence number 2 as your sequence, but it is not necessary to do so, because after round 1, and you can go back to use the index 0. It is okay, because the sender and receiver will not confuse using 1 or 0, because we have only 2 numbers, because we have stop and wait mechanism. 2 numbers is good enough. Okay, so that is RDT 2.1, and there's some discussion right here, but I think I already mentioned this. We stop right here. Okay, make sure you make sure you follow all the final estimation and know what exactly events occurs right now and what is the action should be taken at each state. So you have to I recommend you go around this final estimation once, okay, by yourself, to see if you can explain what's going on at that state and what is the meaning of this event. Okay, that is RDT 2.0. So we will further talk about several different versions of RDT in the later class.